Hi everyone. Today we are starting section 3.8, implicit differentiation. So far, most functions we have worked with have y written directly in terms of x. For example, y equals 5x minus 1. These are called explicit functions. But sometimes x and y are mixed together in one equation and we don't solve for y. Those are called implicit equations. In this section, we'll learn implicit differentiation, which helps us find derivatives even when y is not isolated. Let's take a closer look at these two types. First, explicit functions. For example, y equals x squared plus 1. Here, y is written directly in terms of x. We can clearly see what y equals. So this equation expresses y explicitly in terms of x. That means if we plug in a value for x, we can easily find y, and we can take derivatives using the rules we already know. Now, let's look at implicit functions. For example, x squared plus y squared equals 25. In this case, y is not by itself. Instead, x and y are mixed together in the same equation. So this equation defines y implicitly in terms of x. We don't have y written as y equals something, and solving for y would be more complicated. So why do we need implicit differentiation? Let's look at this equation again. X squared plus y squared equals 25. This equation represents a circle with radius of 5. Now, here's the key idea. If we try to write this equation as y equals something, we would actually get two different expressions for y. Because of that, this graph does not pass the vertical line test, which means it's not a function of x. Even though it's not a function, we still want to find things like the slope of a tangent line. And that's where implicit differentiation comes in. Instead of solving for y first, we can work directly with the original equation and still find derivatives. So in the next part, we'll learn exactly how to take derivatives of these implicit equations step by step.